In the presentation of Cayley's theorem, we focus mainly on abstract issues. So for here, we're going to look at more concrete examples. Now, our setup was we had the left regular action of G on itself. For each element of the group, we're going to have a map pi of G that carries G back to itself. That's defined by pi of G on X is equal to G times X. With this definition, we could think of pi as a homomorphism carrying G to the group of bijections from G to itself. Cayley's theorem then says this map pi is 1 to 1. So we can think of this as embedding G as a subgroup of our group of bijections. If G was finite, then we have that G embeds as a subgroup of some symmetric group with n letters, where n is the order of the group. Now, the point of this, we can always think of a group as a set of symmetries. Okay? It's always at least a set of symmetries of itself. Now, for a few more examples, let's consider the real line. So our group is the real numbers, our set is the real numbers. Here, Y represents real numbers as a set, X represents real numbers as a group. So Y is a point on the real line, X is just going to be how we translate. This situation also applies to the integers, the rationals, and the circle group. It also applies to Z mod n. There we just think of our labels as being numbers on the clock, and then the different actions by elements are just going to be rotations back and forth. Okay, so they're all bijections. Now, when G was finite, the question was, this symmetric group might be rather large, so how do I find an embedding into a smaller symmetric group? What we did, we took a subgroup H in our group, and we considered the left regular action from the left coset space for H back to itself. So we had everything as before. We had that pi was a homomorphism from our group to the group of bijections from the coset space to itself. But pi was not always going to be 1 to 1. So we had to ask, what's the kernel of pi? The answer, kernel of pi was going to be the largest normal subgroup of G that was contained in H. The example that we looked at, we had symmetry group of the square, we had the subgroup given by the identity element and the reflection 1, 3. We saw that the kernel here was the identity. Okay, this group had no normal subgroups besides the identity element subgroup itself. To be explicit, let's take a closer look at the cosets. We have H equal to the identity in the 2 cycle 1, 3. We have 4 cosets, 2, 4H, 1, 2, 3, 4H, 1, 4, 3, 2H. Cosets partition the group, and we'll label each coset A, B, C, and D. Now, we consider the left regular representation, so each pi on G. Each pi on G is going to be a bijection from a set of cosets back to themselves. So we can represent each bijection in permutation notation using A, B, C, and D. So if we work that out, okay, that's a blizzard of symbols, but you'll note, first, pi is 1 to 1, so the kernel is the identity, or there's no doubling of symbols on the right-hand side, and we have that on the right-hand side, these elements are going to form another D8. Now, for another example, let's consider the Quaternion group. So the set here is, I'm going to take the labels 1, I, J, K, plus minus each of those. For the multiplication, for I, J, and K, if we square, we get minus 1. To multiply any 2 distinct letters, we're going to put I, J, and K on a circle, going clockwise. If we multiply clockwise, any two, we get the third. If we go in the other direction, we get the third, but with a minus sign. Now, we apply the same trick. I'm going to label each element, okay, 1 through 8. Here we're going to consider the left regular action of the group on itself. Now, when we work that out, okay, we're going to get elements in S sub 8. We have that pi is 1 to 1. And we can further check that by noting we don't use any permutation twice. Now, the question is, can we do any better? Can we put in a smaller S sub n? And the answer is no. Now, the problem is, every subgroup of the quaternion group is normal. So, if we're looking for a pi that has kernel equal to the identity, the only way that happens is when our subgroup is the identity subgroup itself. As an example, let's try h equal to plus minus 1. So we'll have 4 cosets. We see that the cosets partition the group. And we'll give them labels 1, 2, 3, 4. Now, when we work out pi for each group element, we see that the kernel has more than 2 elements in it. Okay, we see directly that we're using each label twice on the right-hand side. Each of these elements, as elements of S4, have order 2. So the image under pi is going to be a Z2 cross Z2 in S4. One thing to consider, maybe we can do better, but not with this method. The answer still will be, the best we can do is S8. Now, argument will be a little fast and loose. We're going to work with generators and relations. So for quaternion group, for the generators and relations, we'll have 2 generators, x and y. Order of x will be equal to 4. We'll have x squared equals y squared. So y also has order 4. And if we conjugate x by y, we get x inverse. Now, because x has order 4, the smallest symmetric group that we can be in is S4. We need a 4 cycle. So let x be equal to 1, 2, 3, 4. If I square x, we get product of disjoint 2 cycles, 1, 3, and 2, 4. And x cubed is 1, 4, 3, 2. Now, if we're in S4, we have to have that y squared is equal to x squared. So y squared is equal to 1, 3, 2, 4. The only 2 elements with that condition are 1, 2, 3, 4, 4 cycle, and the 4 cycle 1, 4, 3, 2. Now they're x and x inverse, so this can't happen. So we're not going to be able to get the quaternion group in an S4. So let's suppose we're in a symmetric group. Okay, we're going to have S sub n between 4 and 8. We know we can already do it in 8, so we're going to exclude that. If I assume that x is still a 4 cycle, well, we still have the x squared equals y squared. So I'm going to need y to have the 4 cycle 1, 2, 3, 4 or 1, 4, 3, 2. To avoid the mistake we made here, but to still get an element of order 4, I can only attach a 2 cycle that's disjoint. So let's say 5, 6. Well, this doesn't work because now I'll have the xy is equal to yx, and we lose relation 3. So this is not an option. If we assume x is of the form 1, 2, 3, 4 with the 2 cycle 5, 6, okay, we could try this. Here I still have the x squared is equal to 1, 3, 2, 4. So y is going to need the 4 cycle 1, 2, 3, 4 or 1, 4, 3, 2. If we compute yx, y inverse, okay, well we know the 1, 2, 3, 4 is going to commute past whatever we put here because it'll be disjoint. So when we conjugate, we're going to get the 1, 2, 3, 4, 4 cycle. That's bad because if I want the inverse, I'm going to need the inverse of that cycle there. So this can't happen either. So we have to have S sub 8.